Welcome everyone. Welcome to the lecture series on VLSI and microelectronics. It is a subject in 7th semester, BTech ECE. The course code is EC702. I am Paula Sridhar, Assistant Professor, Department of ECE, Guru Nanak Institute of Technology. So let us start the lecture number 6 of this particular lecture series of VLSI and microelectronics subject. So our subject VLSI and microelectronics, having the course code of EC702, it is having total number of lectures 45 and the credit is 4. That is, the total contact hours will be 3 lectures plus 1 tutorial per week. So we are in module number 1, that is Introduction to ICs. So let us have the quick description of the things that we are going to study in module number 1. So we are going to study integrated circuits, advantages, disadvantages, limitations, scale of integration, SSI, MSI, LSI, VLSI, ULSI, Moore's law, scaling of MOSFET, constant field scaling and constant voltage scaling, short channel effects, VLSI design flow, Y chart, IC classifications, that is standard IC and ASIC, PAL, PLA, FPGA architecture. So after this, let us have a quick description of the course outcomes that will be fulfilled after the completion of the particular course VLSI and microelectronics, having the course code of EC702. So the course outcomes are the outcomes that the students will be able to fulfill after the completion of the particular course. So the first course outcome is able to describe scale of integration, SSI, MSI, LSI, VLSI, Moore's law, scaling, short channel effect, VLSI design flow and architecture, and contact gate level circuit with PAL and PLA concept. The second course outcome is able to analyze CMOS inverter voltage transfer characteristics with the parameters VIL, VIH, VOL, VOH, VTH, and based on the knowledge of digital circuit design, methodologies like CMOS, pass transistors, TG, DC-VSL, dynamic logic, NORA, able to construct schematic of combinational sequential circuits, SRAM, DRAM cell using MOSFET. Based on the fundamental concept of the MOSFET characteristics and model, able to calculate value of the resistance of current source, MOS diode, current of current mirror circuit, voltage of references such as the voltage divider, threshold voltage and band gap, emulate resistance of switch capacitor circuit, gain of switch capacitor integrator, and first order switch capacitor filter. This was the third course outcome. The fourth course outcome is, with the help of the MOS transistor model, able to calculate the value of the parameters to design CMOS differential amplifier and two-stage op-amp. The fifth course outcome is able to describe fabrication steps of the ICs and construct stick diagram and layout of the CMOS inverter and basic gates based on the lambda and micron design rules. Sixth is able to calculate gate array dynamic power, short circuit power and leakage power and total power consumption across CMOS inverter circuit based on the derived expression of delay and power. So these were the 6 course outcomes which the student will be able to fulfill after the completion of this particular course VLSI and microelectronics. Now let us see which course outcome will be fulfilled in this lecture, that is lecture number 6. The first one is able to describe scale of the integration, SSI, MSI, LSI, VLSI, Moore's law, scaling, short channel effect, VLSI design flow and architecture, and contract gate level circuit with PAL and PLA concept. So this course outcome will be fulfilled after the completion of this lecture number 6. Also, that's why for your better visibility, this course outcome number 1 is given in red color, so that you can notice that this is the course outcome that will be fulfilled in this lecture number 6. So let us go to the next slide. The next slide is the lesson plan or the lecture plan of this particular lecture number 6. So our paper code is EC702 and we are in module number 1, that is introduction to ICs, that is integrated circuits. And today we are going to study short channel effects, small geometry effects, narrow channel effects and other geometry effects. So let us start the module 1 and also the lecture number 6. So before starting lecture number 6, let us have a quick recap of the previous lectures. So in the first lecture, we have seen the detailed analysis of the VLSI subject and also the course outcomes. Now, we had studied why we need to study the VLSI subject, the impact of the VLSI subject on the field of electronics, what are the applications of the VLSI subject, and how the world is now dependent on the VLSI. That is number of the chips that are integrated in a chip. And as the functionality is going on increasing day by day, and so the VLSI subject is becoming more and more important to the students, because this is the base of all the embedded structures and also all the advanced technologies that are coming out from the VLSI, including the ULSI, then submicron concepts, all like this. In the next lecture, we have studied about the ICs. That is a brief overview of the ICs, advantages and also the disadvantages of the ICs. Next is the scale of integration, which includes the SSI, MSI, LSI, VLSI and the ULSI. Next is the important law in the VLSI subject is the Moore's law. That is, the number of transistors per chips is going on increasing day by day and it is increasing exponentially. Next, we have studied about the scaling of the MOSFET. That is, the scaling of the MOSFET is basically of two types. First one is the constant field scaling and second one is the constant voltage scaling. After the scaling, we have studied the VLSI design flow. That is how the design flow goes on, and also the Y chart. That is starting from which point to which point we should be doing the design. It is described in the Y chart. Next, we have studied the small geometry effects and also the short channel effects. As we know, the small geometry effects are of two types, such as the short channel effects and the narrow channel effects. So we have started with the short channel effects and we have studied the channel length modulation, threshold voltage lowering, punch through, sub-threshold conduction and the velocity saturation. So today we will be starting the narrow channel effects with a brief continuation of the short channel effects. So let us start lecture number 6. So we are having a quick recap of the small geometry effects. Now, due to scaling, the MOSFET dimensions are excessively shrunk. This has imposed the small geometry effects, which include potential problems in the device characteristics and modeling of these effects. These effects are classified into two types, short channel effects and also the narrow channel effects. Now let us go to the next slide. Now the brief discussion of the short channel effects. A MOSFET with a channel length comparable to the source drain junction depth is known as the short channel MOSFET. The short channel devices suffer from several issues that change the characteristics of the device. These issues are known as short channel effects and also DSM, that is the deep submicron issues. Now the short channel effects are of different types, such as the channel length modulation. Second one is the threshold voltage lowering, punch through, sub-threshold conduction and the velocity saturation. All of these are very important in regard of the short note and also in the 5 marks question or also in the broad question. So read them minutely. All this have been described in the previous lecture. Now we will have a small discussion on the velocity saturation. Now the drift velocity of the carriers increases as the electric field increases. However, this does not happen continuously. At some electric field, the carrier voltage saturates. This is the saturation point. See, you can see in this graph. This is the electric field and this is the drift velocity. So this slope is going on and it becomes saturation. It comes to saturation at this point. And this one is the critical electric field. This EC is the critical electric field. Now, this phenomenon is known as the velocity saturation. This velocity of the carriers saturate because at high electric field, the carriers undergoes collision and also lose the extra energy gained due to the increased electric field. The electric field beyond which the carriers start to saturate is called critical electric field, EC. This one is very important. That is a critical electric field. The critical electric field typically varies from 5 volt per micrometer to 7.5 volt per micrometer. If the power supply voltage is 1 volt, MOSFET with a channel length 0.2 micrometer or lesser experiences the velocity saturation effects. Now, in the short channel MOSFET equation, this is the equation of the short channel MOSFET. That is, ID is equal to Q of N into W of small of V of N. This equation overestimates the drain current under the velocity saturation. Now what we can write, this is the equation, that is ID is equal to Q of N into W of V of N. So this can be written as this one, V of N is the saturated drift velocity. Using the saturated drift velocity in this equation, we can write it like this: ID is equal to Q of N into W of V desaturation. So we have got this expression from this expression. ID is equal to Q of N into W of V of N, where V of N is replaced by saturated drift velocity. That is the V of desaturation. So I hope this is clear. Now, hence the drain current under the velocity saturation is given by ID is equal to C of OX, V of D of saturation into W into V desaturation. Now this is the drain current under velocity saturation. This one is important. The drain current under velocity saturation. Now we have finished the short channel effects. Now we will be going to the narrow channel effects. Now let us see what are narrow channel effects. The MOS devices are called narrow channel devices, where the channel width is comparable to the maximum depletion region thickness. So this is important. That is the maximum depletion region thickness. Similar to the short channel effect, the narrow channel MOSFET also exhibits the following changes in the device characteristics. So these are the two properties, or you can say the phenomena of the narrow channel effects. First one is the increase in threshold voltage, and second one is the gate induced drain leakage. So in the later slide we will see the two effects of the narrow channel, that is the increase in threshold voltage, and second one is the drain induced leakage current, or also it is known as the GIDL in short. Now let us see the increase in the threshold voltage. Now this is the cross-section view of the MOSFET, or it also shows the narrow channel MOSFET, in which there are two thick film oxide FOX at both ends of the thin gate oxide layer. Now see, this figure shows a narrow channel MOSFET in which there is two thick filled oxides, that is the FOX, this one, at both ends. These are the both ends. At the thin gate oxide layer. Now the gate electrode partially overlaps the FOX. When the gate voltage is applied, relatively shallow depletion regions are formed underneath the FOX. This at the depletion region is formed. You can see this one. Extra depletion charges are formed here, and there is a depletion region here. Thus, the threshold voltage of the MOSFET increases for the narrow channel devices. So I hope this is clear to you. This happens because to thick field, this FOX is situated here, so at both ends, and that's why the gate electrode partially overlaps the FOX, and when gate voltage is applied, what happens? A shallow depletion region is formed under this layer. You can see this one. This is the extra depletion charges. So this increases the threshold voltage of the MOSFET for the narrow channel devices. I hope this narrow channel effect, that is the increase in the threshold voltage, is clear to all of you. Now let us move to the next slide. That is the gate induced drain leakage. This is very important. When the gate voltage is 0, the MOSFET is off, and hence the drain current must be 0. When the gate voltage is 0 means the drain voltage is the input voltage. So the MOSFET is off, you can say. So the drain current must be 0. But even if VGS is equal to 0, VGS is the drain voltage. I hope you all of you remember that VGS, that is the gate to source voltage, that is the gate voltage, or VGS is equal to 0. That is, but even if VGS is equal to 0, for large drain voltage, there is a leakage current in the device due to the band-to-band tunneling of the carriers. This leakage current is known as the gate-induced drain leakage, or GIDL. In short, it is also known as GIDL. I hope it is clear to all of you. So this was the brief description of GIDL. So now let us go to the other small geometry effects. So there are several other geometry effects which arises due to the reduction in the MOSFET dimensions. So the other geometry effects are, first is hot electron effect, and second one is the time dependent dielectric breakdown. These two are very important because these two are also a part of the small geometry effects. So let us go to the hot electron effect. As the technology advances, the MOSFET dimensions are scaled at a faster rate compared to the supply voltage. As a result, the electric field in the channel region increases. At increased horizontal and vertical electric fields, electrons and holes gaining kinetic energy, that is high kinetic energy, that is you can also call that as the hot carriers, are injected into the gate oxide, and what it causes permanent changes in the oxide interface charge distribution, degrading the IV characteristics of the MOSFET. So you can see there are permanent changes in the oxide interface which causes the degrading of the IV characteristics of the MOSFET. Our main objective is to get a good IV characteristics of the MOSFET, but this degrades the IV characteristics of the MOSFET. So this was the hot electron effect, which arises due to the increased number of horizontal and vertical electric field, which also increases the electrons and holes of high kinetic energy. This high kinetic energy electrons and holes are also known as the hot carriers that are being injected into the gate oxide, which results in the degrading of the IV characteristics of the MOSFET. So this was in short the hot electron effect of the small geometry effects. So let us move to the next one, that is the time dependent dielectric breakdown. Now the gate oxide thickness of the MOS devices is shrunk excessively in the DSM designs. So the vertical electric field EOX will be equal to VDD by of TOX. So the vertical electric field, which is given by this, puts excessive electrical stress on the ultra thin gate oxides. When the thin oxide is operated at high electric field over a period of time, depending on how long the device is operated, there is a degradation in the gate oxide insulator. Eventually, what happens? The gate oxide may break down and the MOS device may get completely damaged. This problem is known as the time-dependent dielectric breakdown. That is also in short TDDB. TDDB. This is the short form of time-dependent dielectric breakdown. You can see how vastly this is affecting. As the gate oxide thickness is shrinked excessively in this small geometry MOSFETs, what happens? The electric field, which puts excessive electric stress on the ultra thin gate oxide layers. Now this gate oxide layers, as the time goes on, it may break down and the MOS device may get permanently damaged. This is very harmful effect, and it is an effect of the small geometry effects. So this were in short the small geometry effects, the narrow channel effects, and also the short channel effects. Mainly all these things occur due to scaling. Due to scaling, what happens? Due to scaling, the MOSFET dimensions are excessively shrunk. Now this includes the small geometry effects, which introduce potential problems in the device characteristics and also the modeling of these effects. Now this arises due to this, that is a scaling. This short channel effects, this narrow channel effects, and the small geometry effects arises. So you can see how these are permanently degrading the device characteristics. So I'm very thankful to all of you for listening to this lecture and hope we will meet soon. Thank you. Thank you again.